Section 3.2, Polynomial Functions and Their Graphs. And our first objective is to determine the characteristics of the graphs of polynomial functions. And every polynomial function will have a graph that is smooth and continuous. And what we mean by smooth is that there are no sharp points. So it's smooth, no pointy parts on the graph. And continuous means you can draw the curve without picking up your pen or pencil. So let's look at a couple of examples and see if we can tell just by looking which graphs are not the graphs of polynomial functions. And we can tell by looking that this one could not possibly be the graph of a polynomial function because it has a sharp point. It's not smooth. So this one is not smooth. So it is not the graph of a polynomial function. When I look at this one, I have to pick up my pencil, right, to draw both parts of the graph. And so this one is not continuous, and it is not the graph of a polynomial function. And so these other two could be the graphs of polynomial functions because they are smooth and they are continuous. So when we are graphing these polynomial functions, we're never going to have sharp points, and we're never going to pick up our pencil as we graph them. They're going to be smooth and they're going to be continuous. Now, the second objective is to use the leading coefficient test to determine the end behavior of polynomial functions. And in order to introduce the idea of end behavior, I have two of our parent functions, the quadratic and the cubic. And what we're going to do is first sketch the graphs of the quadratic and the cubic, and then we're going to see what we notice about the behavior of the function. So the quadratic, f of x equals x squared, we're well familiar with this one now, right? And the reason I like to use these is because we know them well. So there's the graph of my quadratic, and now I'm going to graph my cubic function over here. F of x, or g of x equals x cubed, so that's 0, 0, 1, 1, 2, 8, negative 1, negative 1, negative 2, negative 8. So now let's look at the other two functions that I want us to look at. H of x equals the opposite of x squared. So we know what happens when we put a negative, right, or take the opposite of our parent function. It flips it over the x-axis, right? It reflects it about the x-axis. So we're looking at this graph. And then finally, the graph of k of x equals the opposite of x cubed. That's going to also be a reflection about the x-axis. So if you can keep these four basic graphs in your mind, the graph of the quadratic and the graph of the opposite of the quadratic, the graph of the cubic and the graph of the opposite of the cubic, then you won't need to memorize the leading coefficient test because you'll have it right here in front of you. And what it does is it helps us to determine the end behavior of a polynomial function. And by end behavior, what we mean is if we let x increase without bound as x approaches positive infinity, or as we let x decrease without bound as x approaches negative infinity, what is the behavior of the graph in the ends of its domain? Well, I can see when I'm looking at the quadratic that as x approaches positive infinity, the graph rises to the right, and as x approaches negative infinity, the graph also rises to the left. So the quadratic rises to the left and rises to the right. When I'm looking at the cubic function, as I let x approach positive infinity, the graph rises to the right, and as I let x approach negative infinity, it falls to the left. So the quadratic rises left and right, the parent cubic falls left, rises right. Now, if I take my parent quadratic and reflect it about the x-axis, then it falls left and falls right. If I take my parent cubic and reflect it about the x-axis, it rises left and falls right. So now let's go ahead and dig in a little bit deeper. When I am looking at my f of x equals x squared, the degree of that polynomial, the very simple polynomial, single term monomial x squared, is 2, which is an even number. And, that is what's responsible for rising left and rising right. If I take x squared, if I plug in negative numbers, right, and square them, they're going to be positive. And the more I go to the left towards negative infinity, when I square it, the larger the result is going to be. And as I go towards positive infinity and square it, the larger that result is going to be. My leading coefficient is positive. And what is the behavior of the graph of this function? It rises left, and it rises right. Now, in contrast, my parent cubic, I'm raising it to the third power, right? This monomial with a degree of 3, which is odd, right? What's responsible for this is if I let x approach negative infinity and going this way and cubing it, I'm going to get smaller and smaller and smaller, right? The numbers are going to decrease. If I let x go towards positive infinity and cube these numbers, then the numbers are going to grow very rapidly, right? So it's going to fall to the left and it's going to rise to the right. Negative 1 is negative 1, negative 2 is negative 8, negative 3 is negative 27, right? So because I'm cubing a negative number, it's going that direction. And 1 cubed is 1, and 2 cubed is 8, and 3 cubed is 27, right? So it's going to rise to the right. The leading coefficient, again, here is positive. And what is the behavior of my parent cubic function? It falls left, and it rises right. Now, if I take my parent quadratic and reflect it about the x-axis, the degree is still 2, even. The sign of the leading coefficient is now negative, though. And so now it's going to fall left, falls left, and also falls right. If I look at my parent cubic reflected about the x-axis, the degree is still 3, which is odd. And the sign of the leading coefficient now, though, is negative, right? That negative sign means that it's going to be doing the opposite, right? It's going to be rising left and falling right. Rises left, falls right. Okay, so those 4 very basic functions give us an idea about the possible end behavior of a polynomial function. And what we can do is use what we already know, what we've just established with these very familiar functions, to generalize, as the same pattern holds true for higher degree polynomials as well. So if I have a polynomial with an even degree and a positive leading coefficient, then in the end, it is going to behave like my parent quadratic. It is going to rise left and rise right. Now, with more complicated or higher degree polynomials, what's going on in between might be different, but in the end, it's going to rise left and rise right. If I have an even degree polynomial and a negative leading coefficient, then it's going to behave in the end behavior as x approaches either positive or negative infinity, like my parent quadratic function. If I have a polynomial with an odd degree and a positive leading coefficient, then in the end it's going to fall left and rise right, like my parent cubic. Again, don't care about what's going on in here, only care about as x approaches positive infinity or negative infinity. And then if I have a polynomial that has an odd degree and it's negative, it's going to do the reverse, right? It's going to rise left and fall right. So this, in a nutshell, is your leading coefficient test. And if you just remember those two parent functions, then you can remember what that end behavior is going to be. So now let's put that into practice with some more complicated problems. Use the leading coefficient test to determine the end behavior of each function, and then use this to match each function to its graph. So the first one, f of x equals negative, or the opposite of x to the fourth plus x squared. So we're calling that the degree of a polynomial is the highest power of the variable. The degree is 4 on this one, which is even. The sign of the leading coefficient, now remember, if I'm going to be doing this, they need to be in general form, in decreasing powers of the variable, right? So this is the leading term, and the leading coefficient is negative. So if it's even and has a negative leading coefficient, it's going to fall left and fall right. So looking at the graphs, this is the one that falls left and falls right. So that graph is B. Now, the next one, f of x equals x cubed minus 4x squared. They are in descending powers, right? So this is my leading term. The degree is 3, which is odd. The leading coefficient is positive, so it's going to behave like my parent cubic function. It's going to fall left and rise right. The one that falls left and rises right is C. All we care about at this point is what is the end behavior. We're going to worry about this in between stuff on the next slide. But right now what we're concerned with is what is its behavior in the end. Falling left, falling right, that was graph B. Falling left, rising right, graph C. Odd with a positive leading coefficient. Now, one thing that we need to think about is that this is already factored, right? But what would its degree be? Well, its degree will be equal to the number of linear factors in x that it has. In other words, if I multiplied this out, x minus 3 squared, I would get x squared minus 6x plus 9, right? I don't need to do that to know that the degree will be 2, because there's 2 linear factors in x. I'm going to end up with an x squared. So the degree is 2, which is even. The leading coefficient is positive, so it's going to rise left and right like my parent quadratic. And so, in fact, it's my parent quadratic that's been shifted to the right 3 units, right here, graph A. And then finally, the last example, it's in descending powers of my variable, so my leading term is negative x cubed. The degree is 3, which is odd. The leading coefficient is negative, so it's going to look like my parent cubic that's been reflected in its end behavior. And so it's going to look just like this. It's going to be like graph D, or it is graph D. So we should be able to fairly easily determine the end behavior of given polynomial functions. So this is an example of the kind of homework problem that you're going to see. It says use the leading coefficient test to determine the end behavior of the graph of the given polynomial function. And remember that the two things you are thinking of are what is the degree of the polynomial and what is the sign of the leading coefficient. Well, the degree of this polynomial is 4, which is even. The sign of the leading coefficient is negative. So that tells me it's going to fall left and fall right. So the graph of f of x falls to the left and falls to the right. It's option D. So multiple choice. So now we know how to determine what the function is going to be doing as x approaches positive infinity and as x approaches negative infinity. In other words, what is the end behavior of the graph of my polynomial function? We know it's smooth and continuous. Now we know if it rises left and right, or falls left and rises right, or vice versa, right? But remember all that stuff in between that we wanted to be thinking about. Well, we're going to focus on points that are going to be easy for us to get to, and those are going to be our x-intercepts and our y-intercept. And our third objective is going to be to determine the behavior of the graph of a function at the x-intercepts. And what we're going to want to know is, what is the graph doing at those x-intercepts, if they exist? Well, as we know from our work in Chapter 2, the x-intercepts of a polynomial function occur at the real zeros of the polynomial, right? The imaginary zeros do not correspond to x-intercepts, but the real zeros do. And the multiplicity is a funny little word, right? Multiplicity of these zeros will tell us more. And I've got, again, our parent quadratic and our parent cubic to help us explore this idea of multiplicity of a zero and what it's going to tell us about the behavior of the function. So if I'm looking at the graph of f of x equals x squared, which is my parent quadratic, if I wanted to solve this to find its real zeros, I would set x squared equal to 0, right? Which would mean x times x equals 0. And then using my zero factor property, I would say x equals 0 or x equals 0, right? So my one real zero is at x equals 0. But how many times did I repeat myself as I was solving it? Twice, right? X equals 0 or x equals 0. The multiplicity of this 0 is 2. It is repeated twice. And this multiplicity of 2 is even. Now, what is the graph doing in and around near that x-intercept? Well, as it comes from the left, it comes down, it touches, and it turns around, right? So it touches and turns. At that x-intercept. Now let's contrast that to our parent cubic function, f of x equals x cubed. Well, if I wanted to find the zeros to that, I would be saying x cubed equals 0, and I would say x times x times x equals 0, x equals 0 or x equals 0 or x equals 0. So what is the real zero? It's x equals 0. How many times did I repeat myself that time? 1, 2, 3. So it has a multiplicity of 3, which is odd, right? What is the graph doing in and around that 0, or that x-intercept? It's crossing the x-axis there, right? And let's think about why that might be true. If I have an even multiplicity, and this is very simple, very basic, right? Centered at the origin. To the left of this 0, I'm going to be taking negative numbers and squaring them. That's going to be positive. To the right of this 0, I'm going to be taking positive numbers and squaring them. That's also greater than 0. So it's going to touch and turn around. Now, around the x-intercept here at the origin, negative numbers over here, when I cube them, they're below the x-axis. Over here, when I square positive numbers, they're above the x-axis. So it's going to cross. Here I'm squaring, right? Here I'm cubing. Negative numbers cubed are negative, positive numbers cubed are positive. Negative numbers squared are positive, positive numbers squared are positive. So it's going to touch and turn around. It's going to go across. Now, if I had the opposite of x squared, it would also be touching and turning, right? Because it's going to stay below the x-axis. And if I reflected this, right, and had the opposite of x cubed, it's still going to go across the x-axis there, right? So again, we're going to be able to generalize and say that any real zero that has an even multiplicity, the graph of f will touch and turn around at the x-axis. Any real zero with an odd multiplicity, the graph of f will cross at the x-axis. And it is also true that the higher the multiplicity of the zero, the more the graph tends to flatten out near that 0. So I made a quick video using Desmos, the online graphing calculator that's free and available for your use as well, to show you how that idea of the higher the multiplicity, the more the graph tends to flatten out. And first I graphed y equals x squared. And I see my quadratic, right? And then I graphed y equals x to the 4th. And I want you to notice that the graph gets much flatter close to that 0 for x to the 4th than it does for x squared. They're equal to each other at 1, 1, 1, right? But at a half, if I square a half, it's a quarter. And if I raise a half to the 4th power, that's 1/16, right? So it's going to get flatter. Now, what about if it's an odd multiplicity? Well, there's x equals multiplicity of 1. There's a multiplicity of 3. It's definitely flattening out. Now, what about y equals x to the 5th? It flattens out even more, right? And so I can see that at 1, 1, they're the same, right? But near that x-intercept, the higher the multiplicity, the flatter the graph was, right? So the purple one is to the 1st power, the black one is cubed, and the red one is to the 5th power. And so, you know, again, the higher the multiplicity, the flatter the curve becomes near that 0. So now, for our 4th objective, we're going to find the x-intercepts. We know what the multiplicity tells us about the behavior of the graph at those x-intercepts. So now we're going to look at finding those x-intercepts and then making a statement about the multiplicity and what it tells us about the behavior. So recalling that the zeros of any polynomial function are the roots or the solutions to the equation f of x equals 0, and that each real 0 appears as an x-intercept of the graph, we know our way forward. Looking at this particular one, and this one's already factored for me, right, which is nice in terms of finding my x-intercepts. I have f of x equals x times x plus 2 times x minus 3 quantity squared. The end behavior, well, that has to do with what? The degree of the polynomial and the sign of the leading coefficient. Now, this one's already factored, so I need to count up how many linear factors of x there are, and that will tell me the degree of this already factored polynomial. 1, 2, 3, 4. So if I expanded and multiplied this all out, I would have x to the 4th as my first term. So the degree is 4, which is even. The leading coefficient is positive. So the end behavior, it's going to rise left and rise right. Now my x-intercepts, I find by setting my polynomial function equal to 0 and then using my 0 factor property. So I knew that either x equals 0 or x plus 2 equals 0 or x minus 3 squared equals 0. Here, this one's done, right? My x-intercept is x equals 0. The ordered pair is 0, 0, right? The multiplicity on this one is 1. It only appears once. 1 is an odd number, and so it is going to cross at that x-intercept. If I solve x plus 2 equals 0, I'm going to get x equals negative 2. The x-intercept is negative 2 on the graph. It'll be at negative 2, 0. This one also has a multiplicity of 1. It only appears once. This is an odd number. The graph is going to cross the x-axis at that x-intercept. But when I come to the quantity x minus 3 squared equals 0, well then that's either x minus 3 equals 0 or x minus 3 equals 0. I don't really need to solve those both, right? X equals 3 is the x-intercept. 3, 0 if I'm plotting the point. But its multiplicity is 2 because it showed up twice, right? So multiplicity is 2, which is even, which means it's going to touch and turn around at that x-intercept. And if I use either my graphing calculator or Desmos to graph this particular function, I see exactly what we found, right? So, let me make this a little smaller here. So we said that it will rise to the left, right? It's going to rise left and rise right. We do see that. We see 3 x-intercepts at -2, 0, and 3. At x equals 0, it crosses. At x equals -2, it crosses. And at x equals 3, it touches and turns around, right? But we didn't need to have the graph in order to know that that was going to be the end behavior and the behavior of the graph at the x-intercepts. Now let's look at the next example. Again, reviewing end behavior, I need to know the degree, and I need to know the sign of the leading coefficient. Counting up the linear factors of x, I have 2, x, x, another x, so that's 1, 2, 3, 4, 5, 6, right? If I wrote this all out without using the exponential notation, it would be x times x minus 4 times x plus 2 times x plus 2 times x plus 2. So if I expanded all of this, I don't need to do that. I don't want to do that. I can see that I would end up with 1, 2, 3, 4, 5, 6, x to the 6th in the end. So the degree is 6, which is even. The sign of the leading coefficient is negative. So that tells me that in the end it's going to fall left and fall right. And now I can think about my x-intercepts. So negative x squared times x minus 4 times x plus 2 cubed equals 0. Now, I don't care about this negative sign. In fact, this could be negative 1 million. It won't affect the zeros, right? Only the factors involving x. So, I will care about this in terms of my end behavior. I will care about it as I'm plotting different points. But as I'm thinking about the x-intercepts, the coefficient doesn't affect those. So if x squared is equal to 0, in other words, x equals 0 with a multiplicity of what? 2, then the polynomial will be equal to 0. So that's my first x-intercept. Multiplicity is 2, which is even. It's going to touch and turn. Or if x minus 4 equals 0, or x equals 4, well, what's the multiplicity there? The multiplicity is 1. I only have one factor of x minus 4. So the x-intercept is x equals 4. Of course, this is 0, 0, 4, 0. The multiplicity is 1, which is odd. So it's going to cross at that x-intercept. And then finally, if x plus 2 quantity cubed equals 0, well, I only need to solve x plus 2 equals 0 one time to get x equals -2, and note that I would have done it 3 times, right? So the multiplicity is 3 on that one, right? So x equals -2, multiplicity is 3, which is odd, and it's going to cross the x-axis at that point as well. So how's it going to look different when it crosses here versus here? The higher multiplicity means it's going to flatten out here more, right? So let's take a peek at what that graph actually does look like. So when I look at the graph of this particular function, I see that indeed it does fall left and fall right. It's falling left and falling right. Let me go ahead and make it a different color so we can see it a little better. It's going up and then it comes back down. All right? So it does fall left and fall right. My 3 x-intercepts are 0, 4, and -2. And I can see that it does exactly what we said it would do, right? At 0, the multiplicity was even. It touches and turns. At 4, the multiplicity was odd, it crosses, and it does so fairly straight, right? And at -2, it crosses, but the multiplicity was 3, which is higher. And we can see that it flattens out near that 0. Right? So I didn't need to graph it in order to know that that would be the case with the end behavior and the behavior of the graph at those x-intercepts. Okay, so 2 more examples. For this one, it's already multiplied, right? So the degree is simply the highest power of x. So how you're going to find the degree is going to be different, right? Depending on whether it's already factored or it's not. Since this is not factored, the highest power of x is 3. Well, if it is factored, it's still the highest power of x, right? But the way you think about it is slightly different. So the degree is 3, which is odd. The sign of the leading coefficient is positive. So in the end, it's going to behave like my parent cubic, falling left and rising right. Finding my x-intercepts is going to be more work with this one, though, right? I need to set it equal to 0 and solve. So I can go ahead and factor out an x, because they all have a common factor of x. Minus 2x plus 1 equals 0, right? And now I have a quadratic, which I know how to factor. I'm going to have x and x, right? And I can see that the last term is positive, so I look to the middle. It's got to be 2 negatives, and it's got to be 1 and 1, right? So checking my factoring, x squared minus 1x is minus 2x plus 1. So now either x equals 0 or x minus 1 equals 0. And I would have to repeat that twice, right? Because I could write this, of course, as x times x minus 1 squared equals 0. And then, that's actually a really good exercise, because we can also see that if I was finding the degree in the factored form, I would count up the linear factors of x. So 1, 2, 3. If I multiplied it out, I'd end up with x cubed minus 2x squared plus x. I don't need to do that, though, to know the degree is 3, right? So I have one x-intercept at x equals 0. X equals 0. If I was plotting it on my graph, it would be 0, 0. The multiplicity is 1, which is odd. That's kind of a crazy looking one. So it's going to cross. It's going to do so fairly straight, right? And then I have x equals 1, if I solve this one. Ordered pair, 1, 0. Its multiplicity is 2, which is even. And so the graph is going to touch and turn around at that x-intercept. So for this one, we had to do a little bit more work finding our zeros, right? Okay, another example. F of x equals x cubed plus 7x squared minus 4x minus 28. Again, it's not factored for us, so our degree is the highest power of our variable. The degree is 3, which is odd. The sign of the leading coefficient is positive, so again, it's going to fall left and rise right. Now, to find my x-intercepts, I need to set this equal to 0 and solve. And for this section, if I'm given something higher than a quadratic, higher power than 2, a higher degree than 2 to solve, I'm going to be able to factor by grouping. So if I group the first 2 and the second 2, and if you need a review of factoring by grouping, then go check the review materials. I do see that my first pair has a common factor of x squared. If I factor out an x squared, I have x plus 7 minus 4 is my common factor there. That's going to be x minus, or plus 7 actually, right? Because I want negative 28, and negative 4 times 7 is negative 28. This is equal to 0. Now I see that I have a common binomial factor of x plus 7, so when I factor that out, What am I left with? X squared minus 4 equals 0. Now, this is a difference of perfect squares. X squared minus 4 factors to x plus 2 times x minus 2. So, again, what would the degree of this be if I was given the polynomial already factored? How many linear factors of x are there? 1, 2, 3. The degree is 3, right? Now, solving each one of these linear equations, x plus 7 equals 0, or x plus 2 equals 0, or x minus 2 equals 0, is going to give me 3 x-intercepts, right? So this one, if I subtract 7, I'm going to get x equals negative 7. The ordered pair would be negative 7, 0. Multiplicity is 1. It's going to cross. Oop. Wrote that in the wrong place. It's going to cross, which is odd, and it's going to cross. Now, if I solve x plus 2 equals 0, I'm going to get x equals negative 2, negative 2, 0 if I'm plotting it. The multiplicity is also 1, which is odd, so it's going to cross. And finally, if I solve this one, I'm going to get x equals 2, 2, 0. Multiplicity is also 1, which is odd. It's going to cross there as well. So that one we had to do a bit more work with factoring, right, in order to be able to find the x-intercepts. And again, any one that you have to use factoring to solve for the x-intercepts in the homework will either be like in the previous example or this one that you can factor by using grouping. So the homework for this section I need to take a moment to talk about. For number 6, it says find the zeros for the polynomial function, give the multiplicity of each zero, and state whether the graph crosses the x-axis or touches and turns around at each zero. So I'll write it a little bit bigger. It says f of x equals 5 times x minus 4 times x plus 6 cubed. Now, if I was thinking about the end behavior, the degree would be 1, 2, 3, 4, even. With a positive leading coefficient, it would rise left and rise right. It's not asking me about that in this particular problem, though. It only wants me to find the x-intercepts or the real zeros, right? So I would be setting my function equal to 0. And note that 5 has nothing to do with the zeros or the x-intercepts of this particular function. In fact, I can divide both sides by 5 if I want. And I end up with x minus 4 times x plus 6 cubed equals 0. So, you know, whatever whatever coefficient they have out front, numerical coefficient, you can just go ahead and ignore that when you are thinking about the x-intercepts, and only then, right? Okay, so now either x minus 4 equals 0 or x plus 6 cubed equals 0. This is going to give me x equals 4 with a multiplicity of 1, so it's going to cross. This one is going to give me x plus 6 equals 0 3 times, or x equals negative 6 with a multiplicity of 3, so it's going to cross there as well, right? So now the thing that's a bit odd about the way the homework works is I'm going to show you next. So we decided that x equals 4 is a 0, an x-intercept, and it's going to cross there, and negative 6 is also a 0, and it's going to cross there as well. So it's a multiple choice. I typed in 4 and negative 6. Now, it's multiple choice. So A says there are 3 zeros. The multiplicity of the largest 0 is, the multiplicity of the smallest 0 is, the multiplicity of the other 0 is. Okay, there are not 3 zeros. There are 2 zeros. So I'm going to go ahead and click in this, select B, right? There are 2 zeros. The multiplicity of the largest 0, what it's talking about is the actual value, and 4 is greater than negative 6. So 4 is the largest 0. The multiplicity of that largest 0 is 1. The multiplicity of the other 0, or the smallest 0, which is -6, is 3. So it's not asking you for the actual value of the zeros, it's asking you for the multiplicity of them. And you're going to answer it by thinking about which one's the largest. 4 is the greatest. Which one is the smallest? -6 is the least, right? So think about it that way, and it helps you to solve that particular problem. In the last little bit of the question, it is going to say, determine the behavior of the function at each 0. The graph touches the x-axis and turns around at all zeros. Nope. The graph crosses the x-axis at all zeros. That one is true. Now, if it did something different, then you would select this one. The graph crosses the x-axis at whatever it is, right? And touches and turns around at whatever those x-intercepts are, right? So that's the last little bit of that particular question. So now we're ready to put all of our newfound skills together to graph some polynomial functions. And the set of steps that we're going to go through include to first determine the end behavior using the leading coefficient test. So we'll know if it in the ends rises left and right, or falls left and right, or rises left and falls right, or vice versa. The next step is going to be to find the zeros of the function by setting the equation equal to 0 and solving. And the x-intercepts, if they exist, will be at the real zeros of the function. And we can also use the multiplicity of each real 0 to determine the behavior of the graph at each x-intercept. Remembering that if it has an even multiplicity, then at that x-intercept, at that 0, the graph will touch and turn. If it has an odd multiplicity, it will cross. And the higher the multiplicity, the more the graph flattens out near that point. The third step is a new one. We're going to find the y-intercept, and this is no big deal. We're just going to evaluate f at 0. And then finally, we're going to locate points on each side of each x-intercept to give us a little more guidance in graphing. And then the last step is to sketch the curve, remembering that the graph of each polynomial function of degree n must be smooth and continuous. And a fact that we can take from calculus is that it will have no more than n being the degree minus 1 turning points. And by turning points, what we mean are relative maximum or relative minimum values, where the graph is increasing and then decreases, or decreasing and then begins to increase. So let's put all this together with our first example. And we'll notice that for this particular example, the function is already factored for us, which is very nice in terms of finding our x-intercepts, right? So in terms of the end behavior, remember that we need to think about what is the degree of the polynomial and what is the sign of the leading coefficient. If it's already factored, I'm adding up the linear factors including x. So this is 1, 2, 3. So the degree on this one is 3. The leading coefficient is positive. So in the ends, it's going to behave like my parent cubic and fall left and rise right. Now, finding my x-intercepts when it's already factored is not a big deal, right? Because I'm going to use my zero product property to say that either x is 0 or x minus 2 squared equals 0. So this one's already solved, right? My x-intercept is x equals 0 or 0, 0. The multiplicity is 1, which is odd, and so it's going to cross. And with the multiplicity of 1, it's going to do so in a very straight manner, right? And then for my other x-intercept, I'm solving x minus 2 quantity squared equals 0. So I really only need to solve it once, right? X equals 2, which will be found at 2, 0. Because it's repeated twice, it has a multiplicity of 2, which is even. So it's going to touch and turn around at that x-intercept. Don't have a third one. Now, my y-intercept I find by evaluating my function at 0. So 0 times 0 minus 2 squared is going to be 0, of course, because anything times 0 is equal to 0. And, if our x-intercept is, if we have an x-intercept at 0, 0, that's automatically also going to be our y-intercept. We won't always have an x-intercept at 0, 0, but if we do, we should recognize that that is also going to be the y-intercept. So before we go to step 4, where we're picking points on each side of the x-intercepts, let's go ahead and record what we already know. So I know that in the end it should be falling to the left and rising to the right. I know that I have an x-intercept at 0, 0. That's this one, right? X equals 0. And I also have an x-intercept at x equals 2. And I know that at x equals 0, it's going to cross. And I know at x equals 2, it's going to touch and turn. So now the question is going to be, is it going to touch and turn from above, or is it going to touch and turn from below? So pause the video for a minute and think about that. Is it going to touch and turn from above, or is it going to touch and turn from below, and why? So hopefully you've thought about it and you realize that if in the end it has to rise to the right, it's got to be touching and turning from above, right? If it's touching and turning from below, it would have to turn around and cross the x-axis again, and we know it doesn't do that because these are the only two x-intercepts. All right, so now our last step is going to be to pick points on each side of the x-intercepts. And I'm going to go ahead and pick x equals -1, x equals 1, and x equals 3 to give me a little bit more guidance in completing my sketch. So first, x equals -1, and then I'm going to evaluate it at x equals +1, and then finally, I'm going to evaluate it at x equals 3. So at x equals 1, at -1, f of -1 equals -1 times -1 minus 2 quantity squared. It's -1 times -3 squared. It's -1 times -3 squared is 9. So that's equal to -9. So I'm going to have a point at -1, -9, which fits nicely with my picture, right? Because I said that it was going to be falling to the left. Now let's evaluate at 1. See what we get there. F of 1 is going to be equal to 1 times 1 minus 2 squared. 1 times -1 squared is 1 times 1, or 1. So I have 1, 1. And then finally, at 3, f of 3 is equal to 3 times 3 minus 2 squared. So that's going to be what? 3 times 1 squared. 3 times 1 is 3. So 3, 3. Which also fits with what I expect the behavior to look like, right? So now, we're about ready to sketch. We do know that since the degree of this polynomial is 3, there will be at most 3 minus 1 or 2 turning points. And without calculus, we won't know, unless they're occurring at the x-intercept, exactly where those points of relative maximum or relative minimum values will be. But we have enough to get a really good sketch. So what is it going to look like? Well, it's going to go from this point, right? And we know it's falling left, so it's going to come up. It's going to turn around at some point. We won't know without calculus exactly where that will be. And then we do know it's going to touch and turn here. And then it's going to head up, right? Because it falls left and rises right. So now I can just connect these with this nice, smooth, continuous curve. Coming up, turning around at some point, and then heading back up. So there is my sketch of my polynomial function. And, we were able to do all of that without using any technology at all, right? But I'm going to do a quick video and show you what this would look like if we were using a graphing calculator. So this is the virtual TI-83 that's available for download through Blackboard. And I'm going to go ahead and run the video that I made of the graph of this using the graphing calculator. So the first thing I do is I click the y equals, and then I start typing in the equation. There's my x, open parentheses, x minus 2, close parentheses, square. I can either use the square button, or if it's a higher power or a higher degree, I can use the up arrow, squared. And then I'm going to click the graph button, and then it's going to sketch the graph for me, and it looks very much like the graph that we created, right? My x-intercepts are at 0 and 2, and I can see that it's falling left and rising right. It comes up and crosses and touches and turns and heads on its way back up, right? So we've gotten a very good rough sketch. The graphing calculator verifies for us that we have that we've done it correctly, right? So a fair question that students often ask at this point is, if I have this lovely tool that will do all of this for me, why am I having to learn how to do all of this by hand? Well, because these skills are foundational for understanding what's going on when you get to your calculus course or your pre-cal course in terms of graphing. And it's not enough to just be able to press buttons on a calculator, right? You want to understand, right, how this graph comes about. And going through this process is helping you to understand why those points are being plotted where they are, why this tool is creating the graph in the way it's doing it, right? You want to have a conceptual understanding of the mathematics, right? The reason that you're taking a college algebra course is, well, first of all, to prepare you going forward to your pre-cal, your calculus course, right? And if this might be your last math class, let's say that you're a nursing major and you need stats and you need college algebra. Why are you having to learn how to do this? Well, there's a lot of critical thinking that goes on in the process of creating this graph, right? And the more you exercise those critical thinking skills, the stronger that part of your brain becomes, right? It's like working out, yeah? So the critical thinking that happens in the process of creating this graph is really important. And so, yeah, we could punch some buttons and get the graph right away, but think about all of the mental exercise that took place as we were doing the work to create the graphs ourselves, right? So lots of critical thinking. If this is your last math class, think of it as I'm training my brain to think critically. And if you're going forward with a pre-cal or calculus or business calculus class, you need to understand all of this foundational material so that you'll be able to handle that the more in-depth and complex material that's coming. All right, so let's look at another graph. This one is f of x equals the opposite of x plus 1 squared times the quantity x minus 2 cubed. And so we're going to go through our same set of steps. In behavior involves the degree and the sign of the leading coefficient. The degree, because it's already factored, I'm going to count up how many linear factors of x. I've got 1, 2, 3, 4, 5. So the degree is 5, which is odd. And the sign of the leading coefficient is negative. So I know it's going to rise left and fall right. Now I'm going to be solving for my x-intercepts. So the opposite of the quantity x plus 1 squared times x minus 2 cubed equals 0. And again, as we discussed before, right, the sign out here, the coefficient, which is basically a negative 1, right, doesn't have any effect on the values of the x-intercepts. So I'm simply solving either x plus 1 squared equals 0 or x minus 2 cubed equals 0. And of course, solving this first one, x plus 1 equals 0, x equals negative 1 is my x-intercept. I'm going to plot that at negative 1, 0. The multiplicity is 2 because this factor was repeated twice, right? So it has a multiplicity of 2. Whoop, it already says multiplicity, which is even. And so the behavior is that it's going to touch and turn around. Now, for x minus 2 quantity cubed, if I solve x minus 2, I get x equals 2. I'm going to be plotting that at 2, 0. The multiplicity is 3 because this factor is repeated 3 times, which is odd, and it's going to cross. And because the multiplicity is 3, it's going to do so either like this or like this, right? Not straight across. Remember, the higher the multiplicity, the flatter the graph becomes near that x-intercept. Okay, so let's go ahead and put what we know already onto our sketch. So we know that it's going to be rising left and falling right in the end. We know that we are going to have one x-intercept at negative 1. And it's going to touch and turn there. We know that we're going to have an x-intercept at x equals 2. And we know that it's going to cross there, right? So now, let's find our y-intercept. And because 0, 0 was not an x-intercept, we're not going to have a y-intercept of 0 this time. So f of 0 is equal to the opposite of 0 plus 1 squared times 0 minus 2 cubed. Be very careful here when you evaluate this. First, do what's inside the parentheses, right? So 0 plus 1 is 1, 0 minus 2 is negative 2. You can also type this into your calculator. Negative 2 cubed, 1 squared is 1, negative 2 cubed is negative 8. So the opposite of 1 times negative 8 is positive 8. So my y-intercept is going to be at 0, 8. I'll go ahead and plot that point as well. Zero, let's see, 5, 6, 7, 8 right here. So now I just need a couple more points, right? Because I need points on each side of my x-intercepts. So I'm going to pick one to the left of negative 1. Let's pick negative 2. I'm going to pick another one between negative 1 and positive 2. Even though I do have my y-intercept, I'm going to pick one just so that I can see if it goes up some more or if it comes down here, right? And then I'm going to pick one over here at 3. So the 3 points I'm going to pick are negative 2, 1, and positive 3. So I'm going to pick x equals negative 2. I'm going to pick x equals 1. And I'm going to pick x equals 3. So let's go ahead and see where these points are going to be found. Again, let's remind ourselves what our function definition is. F of x equals the opposite of x plus 1 squared times x minus 2 cubed. Okay. So f of negative 2 is going to be the opposite of negative 2 plus 1 squared times negative 2 minus 2 cubed. Opposite of negative 1 squared times negative 4 cubed. So the opposite of 1 times negative 64, well, that's going to be equal to positive 64, which is off the graph, right? So it is somewhere way up here, right? Which fits because we said it was going to be rising to the left, right? So I'm not going to plot that point, but it's going to be good information for me to know that it's really going to go in. It's really going to be up here, up high, somewhere up here. So now let's go ahead and evaluate at x equals 1. The opposite of 1 plus 1 squared times 1 minus 2 cubed. It's the opposite of 2 squared times negative 1 cubed. So the opposite of 4 times negative 1 is 4. So that one I can plot. 1, 4, right there. So that's some more good information for me. And then x equals 3. It's the opposite of 3 plus 1 squared times 3 minus 2 cubed. It's the opposite of 4 squared times 1 cubed. So it's the opposite of 16 times 1 is negative 16. So I could plot this one as well. 3, negative 16. It's right there. Okay. So now I've got my my sketches ready to go, right? I do know that because this was a 5th degree polynomial, there will be at most 5 minus 1, 4 turning points. So what I've got now is I know that it's going to be touching and turning at negative 1, and it's going to be doing so from above, right? Because I know that at negative 2, it needs to be all the way up here at 64, right? So touching and turning. So it's going to be negative 264 somewhere up here. It's going to come down, turn around. At some point, it's going to turn back around and come through here, right? And then it's going to cross at 2, and then it's going to head on its way back down, right? So I can go ahead now and create my rough sketch. It's coming down, touch and turn, come up at some point, turn around. It's going to cross and then head back down, right? So there's my rough sketch of that 5th degree polynomial. And notice that I didn't make it go straight across here because of that third, the multiplicity of 3. I know it's going to flatten out a little bit there. So I went ahead and I used my virtual TI-83 to create a graph of this one as well so that we can verify our work. And I would encourage you to do this. Do it on your own. Engage in that critical thinking. And then if you want to, go ahead and check your work with your graphing calculator, or Desmos will do it as well. And then you can feel really proud of the fact that you did that by using your critical thinking skills and not just punching some buttons on a device that was programmed by a TI engineer, right? If your hope is to someday be a TI engineer, then you need to be able to know how all of this is happening, right? Okay, so I clear the graph. Go ahead and clear out what we did in the last example, and type in my new function, the opposite of x plus 1 squared times x minus 2 and to the 3rd power, and then graph. And it's going to give us our sketch, which looks very much like the graph that we just made ourselves, right? Then another thing you can do is you can zoom in to, or you can go to zoom and go down to zoom in and click enter. And I'm showing you when you zoom in, you can see the behavior at those two x-intercepts. At negative 1, it touches and turns, and at 2, it crosses, and it's crossing, like we said, it starts to flatten out a bit more, right? And we were able to by using the algebra that we've learned, right? We were able to create that graph all on our own, right? And then we just use the technology to verify. If you plug it in wrong, right, into the calculator and you have no conceptual understanding of how that graph is created, you won't know that the graph is incorrect, right? You won't know that what the calculator is telling you is wrong. That's another reason to understand the math that's behind what the calculator is doing, right? So that you can have a sense of whether or not it's correct, right? Judge the reasonableness of the graph. If you miss a sign somewhere, it's going to look very different, right, as you're typing it in. So, I'm just really trying to make a case for spending the time and understanding the mathematics that underlies this. One final example for this section, and it's going to require us to do a little bit of factoring. So let's think about the end behavior on this one. First, we have to think about the degree, right, and the sign of the leading coefficient. Because this polynomial is in general form and not factored, I can see that the degree is the highest power of x, which is 4, and this is even. The sign of the leading coefficient is positive, so I know it's going to rise left and rise right. Now, solving for my x-intercepts is going to be just a little bit more work, but nothing too bad, right? So x squared times 4 minus x squared. I see that I have a common factor. My greatest common factor is x squared. So I'm going to factor out an x squared, and I'm going to be left with x squared minus 4 equals 0. Now, x squared minus 4 is a difference of perfect squares, right? So that's going to be x squared times x plus 2 times x minus 2 equals 0. So now I've got it factored, and I can see that if it were in its factored form from the start, I would be able to tell the degree by adding up the linear factors of x. There's 1, 2, 3, 4, right? Okay, so now either x squared equals 0, or x plus 2 equals 0, or x minus 2 equals 0. So for this one, I'm going to get x equals 0 as my x-intercept at 0, 0. Because that was a repeated factor, the multiplicity is 2, which is even. And so it's going to touch and turn around. Now, the next one, solving, I'm going to get x equals negative 2. It's going to be plotted at negative 2, 0. The multiplicity is 1, which is odd. And so it's going to cross, and it's going to do so fairly straight, right? And then x minus 2 equals 0 gives me an x-intercept of x equals 2, 2, 0. Multiplicity is 1, which is odd, and so it's going to cross there as well, right? Now, because my x-intercept was 0, 0, I know that my y-intercept is 0, 0 as well, but I can also find that by just plugging in, right? 0 squared, 0 to the 4th, sorry, minus 4 times 0 squared. Well, 0 minus 0 is 0. So my y-intercept is at 0, 0 as well. Okay, so now let's put what we know already on here. We know that it's going to be rising to the left and to the right. We know that we are going to have one x-intercept at x equals 0, right? We know that we're going to have one at x equals negative 2. And we know that we're going to have one at x equals positive 2. Okay, so now when I'm thinking about picking points on each side, I'm going to pick negative 3, negative 1, positive 1, and positive 3. So I'm going to find what the function is equal to at all of those values. So at x equals negative 3, at x equals negative 1, at x equals let's go ahead and do black. X equals positive 1. And then finally, at x equals positive 3. Okay, so for the first one, f of negative 3 equals negative 3 to the 4th minus 4 times negative 3 squared. And I went ahead and plugged that into my calculator, and it's equal to 45. Now I'm going to do x equals negative 1. So f of negative 1 is negative 1 to the 4th minus 4 times negative 1 squared. I don't need a calculator for that one. That's 1 minus 4 times 1. That's negative 3. I won't need a calculator for f of 1. That's going to be 1 to the 4th minus 4 times 1 squared. 1 minus 4 is negative 3. And then finally, for f of 3, 3 to the 4th minus 4 times 3 squared. It's also equal to 45. All right, so now I'm ready to plot my points. I do know that because the degree of my polynomial was 4, there will be no more than 4 minus 1 or 3 turning points. So plotting my points, I have negative 3, 45, that's going to be up here somewhere. I have negative 1, negative 3. Right there. I have positive 1, negative 3. And I have 3, 45 up here, right? Somewhere up here. And so now I can go ahead and sketch in the graph of my curve. I know that it's going to cross at negative 2, touch and turn from below at 0, and cross at 2. And so that's going to give me coming down, turning around, right, at some point, touching and turning around at some point, and crossing. It's going to give me 3 turning points. So I'm going to go ahead and sketch this in with a smooth curve. And I can see that it makes somewhat of a W shape, right? And again, it has 3 turning points. Turns here, turns here, turns here. We know for certain the turning point or the relative maximum is here. We don't know exactly where the relative minimums are without calculus, but we can get a really nice rough sketch. And for this particular function, I went ahead and I typed it into Desmos. And you can see that our graph looks very much like the graph that technology created. So it's a nice verification for us. But we were able to do it, right, without the technology by using our knowledge of college algebra and our critical thinking skills. And one more thing that we could talk about with respect to this particular problem, the function was f of x equals x to the 4th minus 4x squared, right? And I can see that this graph has symmetry with respect to the y-axis. In fact, this is an even function, isn't it? Because if I plugged in f of the opposite of x, I would take the opposite of x to the 4th minus 4 times the opposite of x squared. And the opposite of x to the 4th is the same as x to the 4th. Minus 4 times the opposite of x squared is the same as x squared, right? So